super late at night and I'm quite tired, but I was committed to record this session right now. This session is going to be about chapter 5 of the MPI standard, which is about data types. It is a very, very important chapter. And I tried to come up with as many examples as I could in harmony with the examples that we have in the text of MPI standard. Another thing to notice is that I'm not going to make the same strategic mistake. I'm talking about point-to-point communication, which was something around that episode was around like 58 minutes up to 1 hour. You know, the extent of focus is not going to be around probably not more than 40 or beyond 40 or 45 minutes. I'm not going to keep the videos even up until to that extent. I'm going to keep each episode something around maybe 20 to 25 minutes, and then we're going to extend our episodes as far as we can, as far as we basically need. So each episode is going to be something around 20 to 25 minutes, and if we need more time, then we're going to make more episodes. So this means that episode about data types is going to have part 1, part 2, part 3, as many parts as we need. Okay, so data types. We have already worked with basic data types like MPI double, MPI int, or MPI character. But now we want to extend that knowledge into heterogeneous and non-contiguous data. Heterogeneous means that when you're working with different or mixture of data types, let's say you're working with doubles, integers, characters, everything. Non-contiguous is also self-explanatory. It means that, let's say you have a double at somewhere in the memory, and then at completely a different address, you have an integer. And these double and integer are not next to each other in terms of the memory addresses. So this means that the nature of data that you're working with is non-contiguous. Okay, let's jump into our first example, which is a dummy one, maybe, predefined types. This is int. We populate it with some values, 0 through 4, and then we send it and we use MPI int here. And we receive it with MPI int and with a count of 5, and then we print it simply. So MPI cc predefine and MPI run. Very, very simple example, a dummy one, as I said. Now we're going to work with general data types. General data types needs to have two features. They need to have a basic set of data types, a sequence of basic data types, and they need to have also a sequence of byte displacements. So this means that at which point in memory they start. So, but we can use also absolute addresses, but we're gonna work with displacements for now. Let's say there are displacements in relative or compared to sort of a base address. Okay, so your general data type is going to have a type map, and that type map is a decomposition of all the types involving in your general data type, and associated to each type you have the respective displacement. If you chop off all these displacements, you're gonna left off with a type signature, which basically has information only about the types involving in your general data type. So MPI int, or all those predefined data types, they are also a sort of general data type, and the type map that they carry, for example, for the case of MPI int, is simply int with a displacement of 0. What is extent? Extent of a data type is basically the amount of bytes that it sort of occupies. In other words, in sort of mathematical notation, you can say upper bound minus lower bound. Lower bound is the minimum of the displacement that you have across all the types that are involving in your general data type. But take a look at the upper bound. It's the maximum displacement, but we said that displacement is basically the starting point of your type. So you're going to add to that the size of associated type. What is this epsilon? This epsilon is something which sometimes, some compilers on some machines, they do some padding for alignment purposes. And these are, for example, let's say doubles. they have 8 bytes, and some compilers, on some machines, they associate memory addresses which are multiples of 8. So that is for faster access. That is for faster access. So that epsilon basically considers the amount of padding for alignment. The first example, a very beautiful one. Let's say you have a double at the displacement of 0 and then followed by a character at displacement 8. Why 8? Because doubles are 8 bytes. So 0 through 7, those bytes are going to be filled with a double, and byte number 8 is going to be filled with a character. So assume that doubles have to be strictly aligned at addresses that are multiples of 8. This was what I was talking about padding. So then the extent of this data type is going to be 16. Why 16? Doubles is going to be 8 bytes. Character is going to be 1 byte. It's going to be 9 bytes. But 9, you need to round it to the next multiple of 8, which means that it's going to be 16. So a data type that consists of a character followed by a double, which means if you reverse this thing from character to a double, this is going to also have the same extent, because this thing always needs to round up to the next multiple of 8. Because in this case, we do need that padding for doubles, let's say. Okay, now let's jump into our type constructors with explicit addresses. One very, very important note here is that for those large count versions, when you're working with those _C versions, you need to be careful with these specific ones, like create h-index block, and create struct. You should not use absolute addresses for the byte displacements. The reason for that is normally the byte displacements are having the type of MPI AINT, which is good and proper for addresses. But then those large count versions, they work with MPI count for byte displacements. So care must be taken in these variations that I marked here. So the first and the simplest data constructor is MPI type contiguous, which basically concatenates count number of times the old type you have. C contiguous.c. That's the example we're going to see in a second. So count is the replication count. This is the concatenation count. Old type is the old type that you have. New type is the new type that you want to basically derive. In C, it looks like this. Note that old type is just a type, an MPI data type, but new type is a pointer to an MPI data type. Example, old type is a double at 0 and character at 8. The extent is 16. We already discussed this. Let's say the count is 3 and we want to use this MPI type contiguous. So the resulting data structure is going to be double at 0, character at 8. So this is not going to be at 9, it's going to be at 16 because the extent is 16. Same way, this is not going to be at 25 after the character, it's going to be at 16 plus 16, which is 32. So this is how this sequence of 0, 8, 16, 24, 32, and 40 is basically built up. Now let's go to contiguous. Don't worry about these parts. This is basically, the struct. This is the same example. We tried to replicate this double 0 and character 8. That's the structure, which is a double followed by a character. And we need to create that data type, which has this displacement of 0 for the double, displacement of 8 for the character. So don't worry about these stuff because we haven't talked about create struct. All you need to care about is this MPI type contiguous. We pass in the count. Count is 3, just similar to this example. And then we have the old type, that's this type that we were talking about. And the new type is the one that we are interested to get. And we haven't talked about this one, but basically after each type you make, if you want to use it in communication operations like MPI send and receive, then you need to commit your type before you use it. Okay, we have our buffer. That buffer has the data structure. That's a double followed by a character. It's going to have the count of 3. We populate it uniquely with pi number multiplied by I and character A plus I. These are size information. We haven't talked about sizes already, but all we care about is the send operation. We send the buffer. Note that the count is 1. The count is not 3 because our type contains 3 or concatenates 3 of those old types. So this is very, very important to bear in mind that the new type count that we want to send is always 1. We send it to process number 1. That's the tag 42. And on the receiving side, we receive it and we want to print those information. We haven't talked about these stuff as well, but this is basically after you use your derived type or your general type that you've defined, you need to free the resources that you have allocated. So, okay. Now we say MPI CC contiguous and MPI run. There we go. We're going to discard all these, we're going to discard all these information about the sizing. But I'm going to mention this one, that the extent is 16, just similar to this example that we had on my machine, and my compiler also does this padding. But this is basically the buffer that we have transferred. So this is the general type that we generated with MPI type contiguous, which was a simple concatenation. And we transferred it from process number 0 to process number 1. Rest of the examples are going to be very, very simple. So we have MPI type vector, for example, which has count number of blocks. Each block has this length, and each block is going to be separated with this stride of difference in addresses. And the stride is basically the number of elements that are between start of each block. You see that it's an integer. It's not a non-negative integer like block length or like count. Both of them are non-negative, but the stride can be also a negative number. We're going to see an example in a second. So if you have this pattern again, if you want to use MPI type vector 2, 3, 4, this means count is going to be 2. So you're going to have 2 blocks, block number 1, block number 2. This is the first row and the second row. 3 is block length. So block length is this one, block length or block number 1, block number 2, or block number 3. Maybe not block number, but let's say block length 1, block length 2, and block length 3. And what is this 4? This 4 is the stride, which means 4 times the extent. This has the extent of 16. 4 times 16 is going to be 64. That is why between block number 1, which starts at 0, and block number 2 starts at 64. That's I think now it makes sense. Why do we have 64 here? Because you know that here it starts at 32, and normally if you want to add the extent, 16 plus 32 is going to be 46, right? But here we start at 64 because we want to have 4 elements. So 4 times 16, that's the extent. And that is the distance between the first block and the second block. Let's jump into the example. We do have an example for this one, right? Vector. Again, we're going to discard all these info here for that type. We're going to focus on create, not that one. Create this MPI type vector. We're going to have a count of 2 blocks we want to have. The block length is going to be 3. We're going to have 3 elements of that old type. And we're going to have a stride of 3 because we have 3 elements. And then the next, because these blocks are contiguous in my case, so the stride needs to be 3 in my case. I initialize my data with all this information. So my buffer needs to have 6 elements, and each element is sort of the old type. It's a double followed by a character, a double followed by a character. And then we send that type. Again, the new type, the count must be 1 because the new count already includes all the information about, you have a count of 2 blocks and each block has a length of 3. 2 times 3 is going to be 6. So your buffer is going to be 6. And yeah, new type is going to be, the count is going to be 1. On the receiving side, we just receive it and then we print the information that we received and we free the resources finally. Let's say MPI CC vector and MPI run. So this is also how it looks. And the size is 96. The reason for that is because we had 6 elements and each element was binary with the extent of 16. So 6 times 16 is 96. Okay, next one is very easy. It's H vector. It's MPI type create H vector. It is quite similar to MPI type vector, but the only difference is that the stride in this case is not number of elements difference between the start of each block, but in this case is number of bytes. That is again an integer, which means that it can be also a negative number. So that's the only difference. This is again a very generalization of that type. So this shows, for example, of a block length of, let's say, BL, which spans from 0 to BL minus 1. That's the block length. And then after this block length is over, you're going to have your stride. And the displacement between the first and the second block is going to be displace 0. It's going to be exactly displace 0 plus a stride. So this is how basically it looks. And this count of how many sort of blocks you want ranges from 0 to count minus 1. This is how the general sort of case looks like. So let's take a look at H vector. So again, the same way, we're just going to focus on type create H vector. We're going to pass in count, block length, the stride. The only difference is that the stride this time is not 3, but in turn it's 3 elements, which means 3 times 16, because 16 is the extent. We already talked about it. 3 times 16 is going to be 48. That is why we have 48 here. That is the number of byte difference between block number 1 and block number 2. Again, same way, we initialize it, we send it. Again, the count needs to be 1, and then we receive it and we print it. So MPI CC H vector, and then MPI run. Again, this is exactly the same as the previous one, but this was H vector. Next one is also very simple. It's indexed. So C example index.c. So what is this one? This one takes array of block length, and it takes also array of displacements. So that's the difference with, for example, with vector and H vector. So it takes number of elements per block. So this means that you can have a variable number of elements per block. Let's say block number 1 can have 3 elements, block number 2 can have 2 elements. And you can have also different displacements. You remember that stride was basically a constant difference between each block at the start of each block. But you can now have variable displacements as well. So again, in this case, index is in terms of multiples of old type. It is not in bytes, just like in H vector. And it's also array of integers, so this means that this array of integers can also have negative numbers. This is how the syntax looks in C. And we have a beautiful example here again. So this is the old type map that we had. The extent was 16 for this one. Let's say the block pattern that we want to have is 3 and then 1 followed by a 1. So the first block is going to have 3 elements of these. and the next block is going to have only one element. And then this is going to be our sort of displacement. So the first one is going to have 4 elements, and the second one is going to have 0 elements. So let's take a look at the byte pattern. This is how you call the MPI type indexed. So you start with a double and 64. Why the heck is 64? This is because of this displacement. So 4, we said elements, times 16. That's the extent of this type that we have. A double followed by a character. It's going to be 64. And then the character is 8 bytes distance from this one because double is 8 bytes. So that is why we have all these first 3 sort of elements. So each binary is just one element. So this is one element, this is one element, this is one element. And the reason we have 3 of them is because this pattern is 3. And then the next block, we only have these 2. But why this is 0 and 8? The reason is because the displacement is 0. So that is why we start with this one. This is the general case. We don't care about that. So that is the index version. Let's take a look at it. Again, we don't care about this type, but what we care about is the count is going to be 2. Block length array is going to be 3 and 3. In this case, we have 3 elements and 3 elements again. So block number 1 has 3 elements. Block number 2 has 3 elements. And this is the displacement. So the first one is going to be at the base address. So this is going to be 0. And the second one is going to start with 3 elements difference. So 3 times 16 is going to be 48 bytes. But in index, we work with sort of number of elements difference, not with bytes. So this is how we create our new type. We pass in all the necessary stuff. We commit the type, and then we have our buffer, we populate it, and then we send it. On the receiving side, we receive it, and then we try to print the data. So MPI cc index.c and MPI run. So this is exactly the same sort of example. You see the print output is the same, but we are using different sort of constructors for the general data type construction. The next version is also very simple. It's h-index. You might have guessed. It's similar to index, but it works with this array of displacements work with basically byte displacement. So that's the only difference. Let's go with h-indexed.c. So that is the only difference is this one, that we are working with 0 bytes. This is starting point, and 48 bytes. This is the second block starting point. This is number of bytes. That's the only difference. The rest is the same. So we can say MPI cc h-indexed.c and MPI run. Whoops. So this video is going to be about 23 to 25 minutes. So we have seen the output of this one. I'm gonna break this episode to the next one. So episode 5 is basically finished right here. Follow episode number 6.